Welcome to the last session of the day. I'm Simon. This is work together with a number of folks from the Systems and Networks Labs at the University of Washington, and we're sponsored by NetApp and Google. And one of the main reasons for our research is the recent dramatic increase in storage I/O performance, in particular with things like direct PCI Express attached flash storage devices. And throughout this talk, I hope to convince you that this is posing a new problem for the operating system storage stack, as it's now running in danger of becoming an I/O bottleneck, in particular to applications that do a lot of I/O, like data center servers. And that this is mostly due to the fact that the traditionally shared operating system storage stack is too general. It's trying to be too many things for virtually all applications that are out there that are doing storage, and that this results in a very high computational overhead per I/O operation that applications are executing on top of these stacks. Our solution to this problem is an application-level storage architecture that allows us to integrate the storage subsystem more tightly with applications, such that we can optimize and streamline it per application all the way down to the storage hardware. In addition, we're assuming that storage devices remain on the peripheral bus, so this is where we're perhaps complementary to other lines of recently proposed research where researchers assume that storage will eventually end up on the memory bus. We're taking a more cautious, but perhaps also more immediately applicable approach. Nevertheless, the question remains, how do we structure the operating system and the hardware to allow for such a storage architecture? And that will be the main focus of my talk. A little bit more about the problem first, storage I/O performance. I think probably doesn't take much to convince this audience that storage performance matters to many applications. Here are just a few of them: web servers, file servers, key value stores, and so forth. And on the one hand, help us on the way. Storage performance, especially write latency, has been improving in the recent past and is bound to improve even further into the future. I already mentioned PCI Express attached flash devices. We see Fusion IO's IO Drive 2 here on the right-hand side of the slide. I'm going to use that as a running example throughout the rest of the talk. But there are also flash-backed caching RAID controllers like the Intel RS3 series, where you basically, each write operation goes to a DRAM cache that sits on the controller that can be then efficiently flushed out to flash backing storage in the case of a power outage. So this is great on the one hand. However, unfortunately, on the other hand, CPU frequencies have stalled and are not going to improve significantly in the future. And so if you look at these two curves, on the one hand, the skyrocketing I/O performance curve, and then the flat line for CPU frequencies, you can see relatively easily that executing file system-related code on these CPUs is going to become increasingly more expensive versus the I/O performance offered by these new fast storage devices. And that's the problem. To get even more concrete and to show you where we're at right now with storage performance, we've conducted a little micro-benchmark where we measure file system CPU overheads for a range of popular file systems that you see here on the x-axis of this graph by writing 1 kilobyte, so a fairly small but nevertheless very common write operation for many data center applications, followed by an fsync to make sure that we're not just writing to the file system buffer cache. And we do that over many iterations and then measure the average for these two system calls, which you can see here in microseconds on the y-axis. And this is a stacked bar chart so that we can see the totals for these two operations, which is really the latency that we're interested in. And you can see here for modern file systems that you would want to run, like X3 or X4, we're talking about roughly 30 microseconds of CPU overhead for this rather small write. And then if you want to go fancy and use something like ButterFS, you're going up all the way to about 75 microseconds. Of course, none of this is cause for alarm if you're assuming that your file system is ultimately going to speak to a hard disk drive or to an SSD, both of which have hardware write latencies in the millisecond range. But it does become a problem when we're going to these faster storage controllers. For example, we measured the Intel RS3 caching RAID controller to have a hardware write latency of 25 microseconds. And then Fusion IO reports 15 microseconds for their IO Drive 2. And you can see already from this graph that for most file systems, we're now dominated by the CPU overhead of these file systems versus the storage performance. To understand why that's the case, let's look a little bit more at how today's storage stacks are structured. This is an example for the Linux storage stack, but I'm assuming that other operating systems are fairly similar. At the top here, you have the user-level applications that might have a number of threads that each might execute storage I/O. And they speak to the POSIX API. That's just the standard open, close, read, write API that invokes the kernel where the storage stack sits. And then we have to go through a number of layers within that kernel to ultimately then reach our storage device, which is again depicted by the I/O drive here. Firstly, there's the buffer cache, then there's the virtual file system, then there's the actual file system, X3 or X4, for example. Then there's the hardware abstraction layer and the I/O scheduler, and then finally the device driver. And all of these layers sit directly on the data path of the applications. They're invoked each time an application does an I/O. And this looks like a pretty long list, and it involves a lot of code. The reason for this is, of course, that this storage stack is very general. It's trying to do basically every feature out there for all the different applications. And that results in a lot of indirections. It's also trying to be modular, of course. So we have to do a lot of memory accesses each time we go to another layer. We also have to add code that checks for certain features, whether they're used or not. And then there are system call arguments that might not be necessary for some applications, and so forth. That's one reason for why this stack is kind of heavyweight for these new devices. Another reason is that the stack is also shared among all the different applications within the system. And what that means is we have to add code for security reasons to protect against malicious applications that might impact otherwise benign applications using the stack. So there's even more code that's added. And then finally, there's also more contention on the stack because it's shared among all sorts of different applications. And because it's trying to be general, its data structures are also going to be more complex, which makes it harder to scale the stack with a larger number, growing number of threads that is trying to access it. Finally, the POSIX API is also fairly low level. And what I mean by that is that at the storage stack layer inside the kernel, all we're getting to see is reads and writes from applications. So if we were to optimize the stack for a particular application workload, we basically constantly have to second guess the application because we have no further insight into what the application's original intent with its storage operations are. And this is making it pretty hard to optimize this storage stack. Of course, a higher level API, while desirable, is also pretty difficult to integrate into the stack because, again, due to the fact that it's a shared stack, we would have to add all sorts of higher level API, which again would then grow our attack surface on the stack, which means we would have to put in even more security checks, making it, again, more heavyweight. So that's today's storage stack. So in contrast to this, our storage architecture has a more horizontal split, where we see the applications at user level here on the left-hand side of the slide, and then the shared kernel is on the right-hand side. And what we propose to do is then have a per-application storage stack that is in user level inside the application, basically linked into it as a dynamic link library. And that storage stack has two layers. Firstly, it provides block management as well as caching, and is written against a hardware abstraction layer that is then provided by the device driver, which sits beneath it, that maps this hardware abstraction layer down to the hardware. Now, of course, this user-level architecture only works with some additional support from the hardware, and so we're expecting hardware virtualized storage controllers that we can also just directly map into user space, and that are then provided and multiplexed by the physical hardware controller. I will have another slide after this one that explains a little bit more detail what exactly it is that we expect and how we envision this to be provided. Firstly, though, you can see that now we have a completely application-specific storage stack all the way down to the hardware, which now allows us to streamline it. And due to the fact that we now do not have to worry about other applications using it at the same time, there's only one, we can provide a higher level API on top of the storage stack, which allows us more insight into the application's intents with the storage, and thus allows us to vastly optimize the storage stack. I will demonstrate one of these higher level APIs later on and what we found. Finally, there are still a few things that we're doing in the shared way inside the kernel. The first one is the virtual file system, so basically what provides the global namespace to the user. We didn't want to change anything for the user experience of the regular user of the system, so we still provide a global file name space, and that sits inside the kernel. And then there are a few other resource management tasks, such as space management, free space management, that we also have to do in a global manner. But these are now off the direct data path of the applications. There's nothing inside the per application stack that has to deal with that. Okay, so I'm going to go basically bottom up and go into more details of this stack. So we start at the hardware. What do we expect from the hardware? What's our storage hardware model? So I already mentioned the virtual storage devices. We envision these to basically provide protected command and DMA queues as well as interrupts that we can make available directly for these applications. And this is actually not something for the far future. We're envisioning that this can be provided by current technology. I won't have much more in the talk about this, but feel free to ask me questions later and I can elaborate on what we think is needed. Then, in addition to that, we have virtual storage areas, or VSAs as I will call them, throughout the rest of this talk. And this is basically what the application sees and uses to put its data in. So there's at least one per application. And these map a continuous virtual storage area inside the storage controller. So there's not some kind of DRAM thing. This is inside the storage controller. That map to then physical storage extents in that flash memory. And they are also provided and protected in hardware. Finally, both of these entities, the virtual storage devices and the VSAs, are managed by the kernel. And we're going to see on the next slide, by example, what all the different parts are and how they move. So in this slide, you see here in the lower left-hand corner the kernel, and then you have the physical storage controller. And then we have a little close-up here of its flash memory, and we can see that there's some free space there, and then there are also a couple used regions that are scattered in between. And so let's now assume that a new application comes up and wants to use the storage device. It wants to store some data. It will tell the kernel will see it, and then program the physical storage controller to provide one of these virtual storage controllers, which the kernel will then map into the address space of that application. However, that's not enough. Now the application can still not access any data because it has no access rights. So assume this is a new application. So the first thing that it will now do is tell the kernel to create one of these VSAs and say this is of size 1 gigabyte. That's roughly the granularity with which we expect applications to interact with the kernel. The kernel will then go and allocate some free space, and let's assume that's provided by these 3 extents that it found. We'll then go and program the hardware controller again to provide this VSA mapping down to the physical storage extents. So this is now a virtual range, continuous range for the application. And it will then also ensure to associate the virtual storage device inside the application with that VSA so that it's only this application that can now access that VSA. And the application can then go ahead and use regular hardware operations on top of this virtual storage device to access its storage. And it can do so in any way it likes. It can link in any kind of storage stack. It could use a classical file system, flash-optimized file system, or some higher-level API. I'd like to say a little bit about how we do global file name resolution on top of this now. So it can do anything it likes within this VSA, but it can, in addition to that, give certain objects, any object it likes, but certain objects names. And we envision these names just to be regular file system names. That's a good concept, we think, so why not use it? So it's going to be a hierarchical namespace. And it will register these names with the kernel. And the kernel will now know that it's, for example, in this case, the blue application that is responsible for the storage implementation of these names. And so if another application comes up, say the red application that wants to open, say, the configuration file of this blue application, the kernel will know that it's the blue application and redirect the red application to use the blue application to access the storage. And we have an interface for that. Okay, so now I'd like to change gears and talk a little bit more about the higher levels. This architecture becomes very interesting when you implement higher level APIs on top. And we have done one, which we call persistent data structures that applications can use. What are persistent data structures? Well, you can think of them just as any regular data structure, like a log, a queue, a hash table, or a tree. And they provide basically the same features, except that in addition, they also provide this feature that all of the operations that the application is executing on top of these data structures are made immediately persistent in the flash memory of the backing peripheral. The goals for these data structures are also fairly similar to regular ones. For example, scalability with an increasing number of threads concurrently accessing this data structure is one. But then there are these other two which are important. The first one is robustness versus crash failures. Obviously, we do not want to corrupt the data structure in the backing flash store in the event that we crash while we're trying to flush it out. And then, of course, also very low operation latency, at least a lot lower than the latency of the file systems that I have shown you earlier in this talk. And so we went ahead and actually implemented this whole storage stack and a library of data structures on top. And we did so within the context of the Arrakis operating system, which is a larger research agenda within the University of Washington that has a similar architecture also for the network. And then the overarching goal is to do this for all I/O devices. And in order to implement our prototype, we had to add a user-level device driver into Arrakis for the Intel RS3 RAID controller, which is the controller that we had access to. And on top of the storage architecture, we then implemented a library of persistent data structures, which we call Tenacious D. In particular, we implemented a persistent log within that library. And then we went ahead and used that and took the Redis NoSQL store, which is a fairly prevalent data center application these days. And it so happens that Redis already uses a log to log its operations to stable storage. And so we took it and modified it to use the Tenacious D log instead, which was a fairly straightforward modification. It involved 109 lines of code to be changed within Redis. The interface of these two data structures were fairly identical. And then we took the Redis benchmark that is distributed along with Redis and used the set workload, which is a write-heavy workload within it, and configured it to run on a range of 64,000 keys to values of 1 kilobyte size, so a moderately sized workload. And then loaded this with a number of clients and measured the server-sided latency of this configuration, as well as the end-to-end throughput measured at the clients, and compared the performance of Redis running on top of Tenacious D and Arrakis to that using its own log implementation on top of Linux and on the extended forth file system. And this is what we found. Firstly, the top one half of the slide here is on latency. So we were able to cut the latency for set operations in Linux by 81% from 163 microseconds for each set operation on Linux down to 31 microseconds on top of Arrakis and Tenacious D. And that resulted in vast improvements in the throughput, which you see here on the lower half of the slide in this graph. On the left-hand side, you have the bar for Linux running on top of the RS3 controller. And just to remind you, that controller has a write latency of 25 microseconds. Tenacious D then on top of Arrakis had a speed up of 9x versus Linux on the same hardware. And just to show you that with this architecture, we're now completely bound by the write latency of the hardware, we conducted a little simulation experiment where we took the specification of the IO Drive 2, which is a write latency of 15 microseconds, and looked at what would that result in terms of throughput. And you can see that throughput continues to grow up. And so in summary, we have these new low-latency storage hardware devices out there, and these pose a new problem for operating system storage stacks. Their shared nature makes them become an I/O bottleneck for many applications. I've presented a new storage architecture within the context of the Arrakis operating system that leverages a hardware-software co-design kind of approach to allow for an application-level storage architecture that can eliminate this I/O bottleneck. In particular, we have demonstrated a 9x speedup for the Redis application, and we have high hopes that the stack is going to scale with both vast numbers of CPUs as well as with improved storage hardware performance as hardware designers improve their devices in the future. If you're interested, we also have a website, arrakis.cs.washington.edu, where you can download the source code of Arrakis and Tenacious D. As well as a technical report that contains this result, as well as many others. Thank you very much.
Part where everybody races up to the microphone.
Hi, Aju from VMware. Great talk. I had a question about implementing the application-specific storage stack in the user space. How much context switches do you see between the kernel and the user space, because this is in the user space?
Well,
and one more question,
sure.
Follow on. How would it matter if you had actually implemented the application-specific storage stack in the kernel just by the side of BFS and completely eliminated that path?
Thanks. Great question. The first question is how many context switches we are seeing because we have now implemented the storage stack in user space. So the storage stack is actually linked directly into the application. So each one of these invocations are now regular function calls. They're not system calls anymore. They're not calls to some other service that runs at user level. So there are no context switches involved here. It's really just a function call to a library that implements the whole storage stack and that then goes and programs the virtual hardware that's just register programming, basically. And then the second question was, couldn't you do something similar by modifying the kernel? Now, of course, this kind of goes back to what I said earlier on this slide here, where it would be very desirable to implement more high-level interfaces into the shared stack that sits inside the kernel, but you have to keep in mind that this grows the attack surface on this trusted shared global component. And so that, again, makes it more heavyweight because you have to put in more security checks into the stack. That said, there's also kind of a difficulty in that the stack is already very complex, and adding more functionality to it will make it even more complex. So there's kind of an argument for having a stripped-down stack that is per application, where you can really do what this application requires, and you really only do that, and you don't have to add anything more. I hope that answered the question.
The second part I wanted to know is you could avoid the whole traditional stack and do your own as a case implementation of kernel level.
I see. So you would have to explain to me how you would do this without sharing the stack and without running it in privilege mode, for example, which is another security problem with doing it at kernel level. Sure, we can take it offline.
Jeff Canning, Harvey Mudd College. So you have this global file name resolution thing that routes requests to the right application.
Yeah.
How does that scale to millions of files?
How does that scale with the increase of files? The answer here is that the way this model works is that there's one application which is the holder of the storage. That was the blue application in the talk, and that's the master application. That's supposed to be the application that has to have the fastest access to that storage. I guess the argument is a little bit that other applications that might want to access that storage don't necessarily need that very fast access. So due to this one extra level of indirection, obviously you're going to lose some performance if other applications are trying to access the storage via the blue application. So there is definitely going to be some slowdown there. Scalability-wise, I think the same arguments apply that you could put into other systems that are just single server systems where you have some component in user space. Think microkernels, for example, that manage the storage for you. You can make it scale, for example, by just factoring out a particular server over multiple cores.
Peter Desnoyers, Northeastern. I wanted to, actually my question follows up on something in your last sentence there. So your mention of microkernels, I see two different things here. One of them is, this effort to try to, make as lean a possible interface between your high-performance applications and your storage. But the other is this sort of microkernel-like idea of custom OS functionality for different applications, which different people read things different ways. My take on the last decade or two is that having a small group of people write a single really good, fast piece of software has tended to win in most cases. Now, whether that piece of software is in kernel mode, in a library, or wherever, doesn't necessarily matter. So I'm wondering whether you see a way of actually making this part of the OS, or if it really is destined to be something that's application specific for each. Do you see a way of delivering those benefits across a wide range of applications and not hurting the rest?
Thanks. Good question. That's hard to answer because I think it involves me predicting the future a little bit.
That's the hardest type of prediction.
So in a sense, as a research project, at least, the most interesting part is to put it into user space, because that's where you can really easily experiment. And I think once going into the future, if right now especially, we have this kind of situation where there's a lot of friction in storage performance right now. These numbers are going to change in the future. And I think once this solidifies again, there might be an argument for then putting it, kind of into a more global shared architecture again. However, there is an argument as well that just the overhead of having to invoke the kernel and doing a lot of system calls, I believe Stephen Swanson had worked in that area. They had one of the arguments, not the only one, but it was one of the arguments in there, would already also be very high overhead. There's another work in general operating systems, FlexSC, flexible system calls, where the direct overhead of just invoking the kernel constantly, not just the direct system call overhead, but also the overhead of having to invoke a completely different piece of code and the involved cache misses with that, eventually become very, very high overhead. And as we see storage performance to improve in the future, that alone might be an argument for putting things at user level. Yeah.
Okay, thank you.
Hi, Steve Swanson from UCSD. So you have this thing called a VSA, which is sort of a chunk of flash storage that's allocated by the operating system. And then the applications can access it. And if I squint a little bit, that looks a lot like a file. And you have some way of looking those up internally, and you have protection for them in hardware. So what I'm trying to understand is what, in a fundamental way, is the difference between a hardware-protected VSA and a hardware-protected file? Because it seems like you could do everything with a file and some user space or file system running inside the file that you could do with a VSA.
Yeah, thanks. Great question. I think the most important difference is that a file also has a name associated with it. And so if you were to give different areas of your VSA different names because you would like them to be accessible from other applications, then in this model, you can do that because you can register these names with the kernel. If you're thinking more generally of just a file, then that would have that would be one entity that you name. And then I wouldn't know how you would then access individual pieces within that, because you might have more than just one thing that you want to name within your storage area.
All right, thanks.
So while we're setting up the next speaker, I'll ask one question. I have like 15. I'll start with one. So
take the rest offline.
Architecturally, it feels a little bit, and this might actually be an Arrakis question, in which case we can talk about it later. It feels a little bit like this is an exokernel, right? And that you're putting the I/O stack, and you can have whatever API you want. Yeah. And you should let him set up while we talk to this. Yeah. But at the same, so there's this exokernel piece, and then there's this microkernel piece, which is that any particular storage is owned by one application, which you could then think of as a user-level file server, and everybody else has to talk to the user-level file server. So if I think about this as sort of, looks like an exokernel to the application that owns the hardware and looks like a microkernel to the other applications, is that reasonable?
Yeah, I love exokernels. but that said, so I think, yes, there were a lot of operating systems projects in the early 90s. Exokernel, Nemesis, Spin was probably another project that falls into that category, where people were trying to allow kind of better customization of storage stacks, not just storage stacks, all sorts of I/O stacks for applications. I think the difference now, and maybe also kind of a corollary as to why we arrived at this architecture, is that the hardware is now different. And we were trying to see what we can do with this new virtual I/O virtualizable hardware, and what difference that would make to the design of the storage stack, but then also to the naming system and things like that. And this is why we ended up with this kind of architecture.
Okay, thank you. Let's take our speaker.
Thank you.